Mike from MotoIQ here, and today we're going to build a high horsepower Nissan SR20 DET. Now when I talk about high horsepower, a lot of times people say I use too expensive parts or my power levels I quote aren't that impressive. Well, it's kind of true because generally the engines we build here are for longer duration kind of use. Most of our customers are like track day, time attack, road racing, and drifting kind of people. So their engines have to hold up for more than 10 seconds at a time, or more than just a pull down the street or running it through the gears on the freeway. You know, when you do a track day, even a fun non-competitive track day, you literally spend generally almost a minute at full throttle on any given lap, and you do it for 20 minutes straight. So, you know, this is the kind of hard use that, you know, we build for. If you do drifting, you're bouncing off the rev limiter, going full blast, clutch kicking and everything. A typical drift circuit, the time is like 30 seconds, which is still a lot more than 10. Like if you're at the drag strip or you know, doing a quick pass on the freeway or something. So, you know, when guys go, oh, I run way more horsepower than you all day long, guys that usually make those statements usually don't. So my power quotes are kind of conservative and therefore the toughest of end use. Maybe the only thing that's tougher is like off-road or offshore boats, but you know, not too many of our customers do that. So with that being said, I'd like to talk to you about a 500 horsepower safe SR20 that's going to be used in our project Do It All S13. So this car is being built to do road race, time attack, and be able to drift. It's kind of a tall order, but I think we can do it. So the basis of our engine build is something that's really bulletproof. You know, we're hoping to get at least 2 seasons out of it in between rebuilds, which is pretty respectable. And we started at the, you know, very base with really solid components. We started off with the block. The block has been subjected to CTP cryogenics, latest aluminum-specific cryo process. Now, CTP has just perfected this a few months ago, and they're kind of secretive about it, so I'm not sure how the metallurgy of this all works, but it's a new process that's supposed to significantly strengthen aluminum. I think this is something like an extension of the post-heat treat process, kind of like when you hear about bringing aluminum into a T4 or a T6 state. It's something like that, so I think it's a sort of like post processing refinement of heat treating. So, you know, that's a bunch of scientific sounding stuff. So just Google T6 state for aluminum and you can kind of see what I'm talking about. I'm not sure, like they won't tell me exactly what the difference in the process is, but they showed me some data with really good results, and it's kind of exclusive to them. So anyway, the block was subjected to this new cryogenic treatment, and we took it over to our friends at D-Sport. They have some pretty sophisticated boring stuff. So it was bored with a torque plate and a rear torque plate. Now in an SR20, they distort quite a bit with cylinder head torque. And we're using studs, so you know that I'm not a super huge fan of studs unless you're going for an all-out motor. The reason for this is on an aluminum block in particular, the aluminum grows with heat at twice the rate the stud does. So your stud is already tightened down more than stock, which contributes to distortion of the block and everything. And when everything starts growing with heat, you get even more clamp load. Maybe it could be beyond you know, what's right. Like you start to distort your deck and you get point load around the bolt holes. And stuff like that. So you can actually lose clamp even though you're clamping harder. And you can also get bore distortion, so you get less ring seal and potential scuffing and things like that. So what I always say, if you must use studs, you know, like you have to use the torque plate, and you have to have the studs right to the max level of specified torque, so at the high end of their range, and do all the machining like that. So, you know, in an SR, even using regular bolts, the bore can distort as much as 1.5 thousandths, which can be about almost half your total piston to wall clearance. So it is really important to use a torque plate. Also, you want to have like a plate on the back of the engine, because we found that just bolting the transmission on can distort cylinder number 4 about a thousandths, or you know, 1.2 thousandths even. So this block does move around a lot with torque, so it's important to do proper machining. Now, for our cylinder wall finish, you know, if you know Lake Speed Jr., he's engineer for Speed Pro. You might want to watch some of his videos on proper cylinder wall finishing on YouTube, and he has it down to a science. So we followed his recommendation for bore finish, which is a little bit different from what we were typically doing. So for a turbocharged engine, he uses like a rougher stone that's typical, and he uses a plateau hone to knock the peaks off of the hone finish so you don't chew up your modern high tension rings. The reason for this is the coarser finish retains more oil on the cylinder wall for a boosted engine, so you get a little bit more lubrication for your rings and your piston skirts, even though you're running higher cylinder pressures and you're putting more side load and everything. So our cylinder wall finish is per his recommendation, and it's a little coarser looking than what you're used to seeing in some of our videos. So we're going to be experimenting with that. In addition, after boring and honing with the correct fixturing, we subjected our bores to WPC treatment. If you watch some of our videos on our series engines, we do this a lot. WPC is kind of like microblasting. They blast the surface with a special secret ceramic media that's really small, and they mix it up with some dry film lubricant, so you get a really small, really small surface imperfection finish with some dimpling. The dimpling is also good for lubrication retention. It's really smooth, and you have dry film lubricant blasted into the surface of the metal. It also does localized work hardening and grain refinement, so you reduce friction and your wear is greatly improved. So on our series engines, we do WPC treatment on you know, anything that rubs. The power gain is really hard to measure, but for sure I can tell you that just about any rubbing surface lasts twice as long with WPC. So it's not uncommon for our engines to go a lot longer between needing refreshes than with other builders, you know, if people opt for this option. Cryogenic treatment can also lend to improved wear. So for steel, like in the cylinder liners, the cryogenic treatment can turn some of that remaining austenite in the crystalline structure into martensite, which is a harder, stronger surface. You know, it's sort of like a function of heat treating, and you know, this is kind of no bullshit documented science stuff. A lot of people have seen our videos and accused us of selling snake oil, but you know, like the process of cryogenics is a legitimate metal treatment, just like heat treating. The cryogenics also stress relieves everything, which is also good for you know, dimensional stability and everything, which is kind of critical in the block. We've done extensive videos on both the WPC treatment and CTP's cryogenic treatments. So, go to our YouTube channel and use the search, and if you're curious, and you can see in quite a bit of detail how these processes work. But we did make extensive use of it. We cryogenic treated the girdle and the main caps, and sometimes you see dimensional changes because you're changing the crystalline structure of the metal. Things move around and grow. So we carefully measured the main bores and to see if it needed a line boring after cryo, but everything was okay. And when we tightened everything down with the studs, the main bores were round and just about the minimum of Nissan spec, which is good for bearing clearance and maintaining good oil pressure. So everything was cool with the block. Everything's pretty strong. Pretty happy with how the block came out. So for studs, we didn't use ARP studs. We used MOSWorks proprietary stud. MOSWorks is one of the top SR20 builders in the country. So I think the studs, these particular ones are like an ARP 2000 material. Pretty strong stuff. It's not as strong as 625, but we're only making 500 horsepower, so we don't have to overkill it. But what I particularly like about MOSWorks is they have these bottoming ends. So when you tighten them down the block, the ends bottom out in the hole, so you can actually tighten the studs into the block. And a lot of the SR20 studs on the market don't have that feature, and I think it's a pretty important feature. They also have rolled threads, which are stronger than cut threads, and I feel like these MOSWorks studs are the best on the market for the SR20. And you can probably get custom studs that have some of the same features, but hey, MOSWorks did it for you, so I recommend them. I guess some other interesting SR20 specific stuff we did is the oil pump. So in the past, I've had the oil pump pressure relief valve stick and damage our engine. Something about the way the relief valve goes in the bore in these SR20s, it can hang up on the relief port. So what I do is I inspect the relief port for burrs, and I round it off with a deburring knife. I also check the bore for any imperfections. Then I WPC the housing to make sure it's all smooth and the relief valve can't stick. I also cryogenically treat and WPC treat the oil pump gears. SR20s don't particularly have a problem with breaking these, but a lot of engines do. And I think it's always a good precaution to use a little care in your oil pump gears, whether they have a tendency to break or not. It also reduces friction. One of the things the WPC also does is when it makes that hard compressed layer, it's making a surface where it's really difficult for cracks to propagate. So WPC treatment generally increases the fatigue life of a part by about 100%. And this is all good stuff that can't hurt on an oil pump gear. I also cryogenically treated and WPC treated the pump pressure relief springs so they slide really smooth. And WPC treated the pressure relief valve plunger itself. So everything's going to work nice and smooth, and there's going to be no chance of this guy jamming and causing you to lose oil pressure. For the rest of the bottom end, the crank we used is this nice stroker piece by K1. It's 91 millimeter stroke, so it's up 5 millimeters from stock, which will give us a displacement of just under 2.2 liters. I think this is a beautiful crank, and it's a great piece for the price point. It's machined out of a 4340 forging, so that's like a high nickel, high molybdenum alloy. The nickel gives it really a lot of strength and toughness and resistance to repeated impact type loads. So that makes it the perfect material for crankshafts because they feel that kind of load. Usually SR20 cranks, are beefy to begin with. Like the stock crank is pretty strong too. But, we wanted to stroke the engine, give it some more low-end torque. Since it's a drift car, we wanted to be torquey, and we don't really want it to rev too high because of SR20 valve train stability issues. So we're not going to scream it to $9,000 or anything, but we're going to have it torquey and responsive and more displacement. When you look at this crank, you could tell that the counterweights have been lightened and profiled. The crank probably weighs a few pounds less than stock for that reason. And they also have this aerodynamic profile, so the crank can cut through the windage cloud in the crankcase, so you have less windage power losses. The journals have a generous fillet on them. When cranks crack, it's always in the corners here, so having this fillet here actually really helps the strength and fatigue life of the crank. The crank has a nice micropolished surface, as is from K1. Like we usually micropolish all our journals, but hey, this one came like that. The crank is also post machined, heat treated, straightened, and shot peened. So shot peening is sort of like WPC, but uses bigger media. So it's a hard iron shot, shot at a high velocity. WPC might only refine the surface of the metal maybe 8/10 or something into the surface, but shot peening with the bigger media can actually refine the grain and everything maybe as much as 3/1000 into the part. So shot peening really helps fatigue strength and everything, and it's a good process with free strength basically. Even though this crank is stroked, SR20 cranks are pretty beefy and they have a lot of journal overlap, which lends to stiffness. And even with the stroking, we still have some journal overlap, and with these generous cheeks and strong material, I think this crank is going to be strong as heck, and we're never going to have problems with it. So, there's other stroker cranks for the SR available, especially out of Japan, but I think this K1 is a great value. It's a beautiful crank, and it's full of features, so can't go wrong with that. For connecting rods, we're using Wiseco's boost line rods. These rods are specifically designed for the compressive load that a boosted engine creates. So when you look at the kind of different side profile here, or face profile, you can see it's kind of like some little triangles right at where the big end of the rod transitions to the beam. Wiseco used finite element analysis and put a lot of compressive and bending load on the rod, and they determined that this shape was optimal for a turbo type load, which is going to be compressive and bending a lot. This had strength and stiffness over, conventional beam configurations. So, it looks cool, and it's not just for looks, it's for functional, and it's highly engineered. It's unusual. I haven't seen this, but I've seen the FEA output, and it's pretty good. We got the optional boost line that uses the ARP custom-aged 625 rod bolts. So these are considerably stronger than the ARP 2000 type rod bolts that are typical. Rod bolts are the highest stress part of a rod and can be the cause of failures. So, spend a few bucks extra and put the best rod bolts in. It has like a shot peening, which gives all the same fatigue life improvements that we saw on the crank. We also subjected the crank and rods to CTP cryogenic treatment. For like ferrous metals, the cryo converts a lot of the austenite into martensite. As we said before, it goes from a face-centered cubic to a body-centered cubic structure, which is harder and stronger with better tensile characteristics. We also WPC'd the crank and the rods. We did the whole rod and we did the bolts. This is a further refinement of the shot peening process, and for the small end of the rod, it makes everything slipperier. On the bolts, it should help fatigue strength and help us get more accurate torque. You know, I think it's all wins for not that much more money. So we have a turbo-specific rod. You know, it might be slightly heavier than, you know, like a naturally aspirated spinning type rod, but it's only a few grams, and the strength in a high boost, heavy compressional loaded turbo motor is going to be worth it, I feel. So for the pistons, and I think these things are beauty. I worked with the guys at JE Pistons, and we came up with maybe the ultimate SR piston. So we have a higher compression height for the stroke, and we're able to keep it out of the oil ring, which is cool. We use JE's FSR asymmetrical forging, which I think is really sweet. If you see, the thrust side of the piston has a nice full face, but the non-thrust side that's not so heavily loaded has a narrow face. So you have a wide face where the load is for better wear, and you have a narrow face on the unloaded side for less friction and less weight. So you kind of have the best of both worlds. It's also a strut type forging, so you have all these like buttresses for strength in the pin boss area. We specified some custom features, like we have dual pin oilers. These pin oilers get oil from the oil rings, and the oil rings act like a pump, so it feeds the piston pin a continuous supply of oil. So you never have galling or anything that could lead to pin boss or pin failure. When you look at the dome configuration, we did this so you have quench. The quench lines up with the quench pads on the combustion chambers, so you have a turbulent mixture with less propensity to detonate. We did the dome or the dish volume, so we have about 9-to-1 even with the stroke. JE did anti-detonation grooves from the top of the piston to the number one ring. Now these anti-detonation grooves kind of form, they're for two different things. One of them is detonation can really give a lot of localized heating, and since aluminum expands a lot, sometimes it expands so much when you see detonation that it eats up the piston wall clearance, so this part of the piston, particularly around the exhaust valves, expands and starts to scuff and dig into the cylinder walls. You've probably seen engines that have been detonated and they're all chewed up, and the cylinder walls are chewed up in this area. So what these grooves do is they give the aluminum some area to expand into, so it's less likely to scuff. Also, the grooves act like sort of like a labyrinth, so the shock wave of detonation doesn't get into the number one ring and cause ring flutter and skipping, and which could lead to poor seal and accelerated number one ring wear. We have lateral gas ports here too. So the way rings work is by pressure differential between the top and the bottom. And the lateral gas ports help some of that combustion pressure get behind the number one ring and help it seal. Now, you've probably seen some drag racing pistons and the gas ports are in the top. But, that gets a lot of pressure and sticks it behind the ring. But in road racing and longer duration things, those ports clog up. And they also probably do too much pressure, which leads to accelerated ring wear in the case of road racing. So we have our lateral gas ports to help the seal. We have a pressure equalization groove here, and what that does is any gas leaking past the rings, it has a little reservoir to go into and kind of normalize the pressure before it gets behind the number 2 compression rings. So, it helps the number 2 ring seal better, gives it a little reservoir of pressurized gas to seal with, and that all helps at especially at high RPM. Our oil ring is like typical, except it's a thin, low friction one, and it pumps oil into our piston pin area for the pin oilers. We also have thermal barrier coating on the dome and dry film lubricant coating on the skirts. The thermal barrier coating will protect the piston in case of detonation, keeps the piston cooler. The skirt coating kind of helps prevent scuffing and gives a little bit of cushion of the aluminum against the cylinder wall, reduces friction. We had the piston WPC treated, but you can't WPC then coat because the coating won't stick. So we masked the piston off, and we WPC treated the ring area and the pin boss and the pin bore, but we masked off the coated areas. So, like we have the benefits of WPC, which are better wear in the ring groove area. Ring groove wear is important for compression seal. Also, the rings will resist micro welding better. So even in extreme conditions, they won't get stuck. And those are the main advantages: long life and the avoidance of micro welding. The piston was also subjected to CTP Cryogenics new aluminum treatment. So the piston pin is a pretty thick wall pin that's designed to take boost pressure without bowing. For like a boosted engine, you don't want to do thin wall and taper walled pins like you might on a naturally aspirated motor for less weight. You want to have full length and you want to have full thickness. This is because with the boost pressure, you don't want the pin to bow, because then it could grab onto the small end bushing and spin it out of the rod and cause engine failure that way. And you also want the full support of a full width pin, so your pin boss has like a lot of bearing area, so you don't have pin boss failure. We WPC treated and cryo treated the pin for smoothness, long life, and extra strength. Our piston rings are super thin, low tension rings. Before in the old days, if you wanted to make an engine with durability, you use thicker rings and they would wear better. But technology's gone way past that. So nowadays you want thin, low tension rings that actually seals better and gives longer life. The low tension reduces friction, and it also reduces the tendency for the rings to flutter and lose seal, like right when you're coming to TDC and you're reversing direction. And this is because the ring is a lot lower inertia and it tracks better. For long life, the number 1 ring is steel instead of the traditional iron. It's stronger and more ductile. It's also nitrided, so that's a really hard skin surface on that for longer life. The number 2 ring is iron, but it is thin and low tension, and it has a Napier profile. A Napier profile is kind of this, it has almost like a blade on its face, and this blade gives more point contact and kind of wears into the cylinder quicker and conforms to the cylinder quicker. So the number 2 ring, its job is to conform to the cylinder quickly, break in quickly, and just add that little bit extra seal. The number 1 ring is to do most of the primary sealing and do it for a long time with good life. So the oil ring is a standard low tension with like a thin rail, nothing too special other than it's low tension. So this thing has a pretty high-tech ring package. For bearings, we're using ACL bearings. The ACL bearings, we're also using a ACL thrust bearing. The ACL bearings are a tri-metal type of bearing, so you have your steel backing. You have a harder underlay, which is probably like lead, but it has a high tin and antimony content. I don't know the metallurgy exactly, but it's something like this. Tin and antimony are agents that make lead a lot harder. So if it's harder, it has more capacity to bear load without smearing out and grabbing on the crank, makes it less likely to spin. This hard layer does most of the heavy lifting. There's probably a lot of copper in it too, because copper gives hardness and strength. And then there's a surface layer which has a higher lead content that's softer. This gives more what you call embeddability. So like if you get dirt particles in the oil, things like that, they can actually embed into the soft surface and not go around like sandpaper and damage your crank. So they kind of give the bearings some more forgivingness. But the base layer, which is copper, tin, antimony, and some lead, does the heavy lifting as far as taking the load on the bearing. And then there's a zinc overplating on the top, which gives it corrosion resistance and resists scuffing when the engine is first being started and getting its initial break-in. In addition, we got the bearings WPC treated, and WPC actually does a lot on bearings. Like it kind of gives it some of that microforging and gives it a really smooth surface. And you know, in testing, some OEMs secretly do this process on their bearings too, but it's been determined that generally WPC increases the load bearing capacity of a bearing by about 20%. So we'll take that. It also reduces friction, so we'll take that too. WPC is a really versatile process, and we use it on about everything that rubs and wears. We used a crankscrapers.com windage tray and scraper. So this bolts right under the girdle, and its job is to strip off the windage cloud off the crank and the rods and get all that oil and return it into the pan. It actually has like this Teflon piece that just about lightly rests on the crank. It kind of self-clearances in. So it's got to strip every bit of that oil cloud off. Now this part's kind of important because with a stroker crank, these slots here are going to be in a different spot than stock. So it'll enable us to slide this around and get those clearances just right, even with a stroker. You can see this part has the metal scrapers, and it has this one-way mesh. So once the oil gets stripped off the crank and rods, it returns it to the pan. The turbo engine, you're always dealing with oil consumption and spitting oil, and you know this will return that oil to the pan, reduce oil consumption. On racing SR20s, we see a marked decrease in oil consumption, and the oil temp generally drops 10 to 15 degrees, so this thing works. It's also said to improve power by about 5 horsepower, but that's kind of hard to prove. But I mostly use it on raced SR20s to get that oil in the pan and keep it cooler. We're using a ATI super damper. You know, being the stroker engine, it's going to have more torsional vibration and torsional whips, so it's good to have a better damper than stock. This ATI is cool because you can build it and change all the elastomer elements in. I mean, you don't have to do it all the time, but probably I would change the elastomers every rebuild cycle. And the most important thing is it's smaller in diameter, so it underdrives the water pump. SR20 water pumps, they have a problem. They like to cavitate at about 6,500 RPM, so the flow in the water pump can go almost to zero at high RPMs. And this is why like a lot of SR20s have stubborn overheating problems. So the smaller pulley will drive the water pump slower and help keep you out of that cavitation zone. We also have a bigger underdrive water pump pulley. So, now the water pump won't cavitate to like just over 8,000. I think if you're going to road race your SR powered car, these two things are critical, and you got to do them. We got a MozWorks front pulley bolt. Now SRs aren't known to throw their front pulley, but with a stroker engine and more torsional vibration, who knows? MozWorks thought it was important to come up with this heavy duty bolt. Doesn't cost that much, so why not? We're also using ARP high strength flywheel bolts for the same reason. Now, we about covered the bottom end, so now it's time to get into the top end. Like SR20 heads don't flow that well. Like with a turbo engine, maybe flow's not that critical, but we're trying to make power with less boost. So our friends at D-Sport, they ported the head. Now, to keep our response good and everything, they didn't hog the ports out huge, but where the SR20 has a lot of problems is it has a really tight short side radius in the ports and a lot of restriction from the port bowl into the port itself, so they did most of the work down there. So it'll keep our port velocity high, and it'll keep, like our bottom end good. So I think we probably really picked up flow without sacrificing velocity, so it shouldn't hurt low end at all. They polished the chambers and did some cuts to unshroud the valves, which is critical for low lift flow. They also did a Newen valve job. Now, most of our valve jobs are Newen, and I really like those because instead of stones or cutters, it uses a CNC machine and cuts a continuous radius to the 45 seat and then cuts a radius away from that. And we found there's like sometimes 50, 60 horsepower to be found over like a conventional 3-angle valve job by going to a Newen one. The Newen also makes this cool radius that totally unshrouds the valve in the entrance to the combustion chamber, and it's some of the reasons why it makes more power. So the bottom cut of the Newen machine goes up to the porting, so it's a nice smooth transition from the valve seat into the port itself. We went to 1 millimeter oversized valves, and we're using our valves are made by Supertech, and they're like works of art. Like our exhaust valve is made out of Inconel, and it has a hollow stem that's sodium filled. So the sodium filled stem sucks heat out of the valve and lets the valve run cooler. Now the exhaust valve is usually the hottest thing in the combustion chamber, and often it's the site where detonation starts. So if you can keep the exhaust valve cooler, like you can actually have more detonation margin, which helps your reliability. Now you look at the exhaust valve shape, you can see that the stem size is reduced where it hangs into the port. This actually helps flow quite a bit. I mean, there's been some studies where it helps like 8% of your total flow. I don't know how much it's going to improve the flow in an SR20, but it sure can't hurt. Also, the exhaust valve has a tulip contour, so when the flow is going this way out of the engine, the tulip contour helps improve the flow. And also the 45 seat, the transition from the 45 to the tulip is really smooth, so you don't have to worry about back cutting the valves or anything. And they're also kind of hogged out down at the bottom for lightness. It's a really cool valve, especially for a turbo motor. Now the intake is made out of nitride, it's stainless. It has some of the features of the exhaust valve, like the reduced stem. The shape of the intake valve is what we call more of a nail head. It's when the flow is going this way into the combustion chamber, this flatter contour actually helps flow. The valve's nitrided for long life in the stem, and both the intake and exhaust valve have been WPC treated for less friction and longer life. D-Sport did our valve job, and they did some tricks like they actually cut the valve seats and did the valve job with a torque plate on the head. They found that bolting the head onto the block actually distorts the head quite a bit. And if you use a torque plate on the head, they found that leak down's quite a bit better, and break-in's quicker, and overall durability of the valve job improves. You know, like, this is kind of an innovation that they do, and then I've seen some engine builders in Japan do, but Mike Ferrara there tells me it'll make a big difference. We also used SuperTech bronze valve guides for durability and low friction. SR20s, being finger follower motors, put a lot of side load on the valves. So, you know, like better valve guides, WPC treatments, all going to lead to longer life. So this is a pretty cool little head, and we think it's going to do pretty good in power production and get us power at lower boost. For the head gasket, we're using a Apex head gasket, and this is a folded stopper type head gasket, which is about the best head gasket you can get for boosted operation. It's an MLS gasket with 3 layers of steel, but the center layer actually has like a fire ring that the inner layer folds over. So it has a ring of steel with the folded over midsection that puts more sealing pressure right around the bores. So it's probably about twice as hard to blow this out as your conventional MLS gasket, and you know, like an order of magnitude better than the stock Nissan composite gasket. So this is a really good gasket, and I think we're not going to have any sealing issues. For the valve train, we're using Jim Wolf Technology C1 cams. The Jim Wolf C-Series cams have fast ramps and a lot of lift, and they have way more area under the lift curve than I think any other SR cams on the market. So per degree of duration, they make the most area under the curves, so they always have the best power and torque out of any SR cams we've tested. They do a lot of analysis, so they also have really good valve train stability. This is important for a drift car that you're banging off the rev limiter a lot. I really think JWT did their homework and produced the best SR cams on the market, and we recommend them over anything else, really. We cryogenically treated, and WPC treated the cams as well. What else did we do? The C-Series cams have springs. The springs are matched to the harmonic characteristics of the cams, so they counteract spring surge. The JWT springs can actually get a lot of surge control with a really low installed seat pressure. The seat pressure isn't crazy high, but they really help prevent surge and valve float. You know, like, you don't want to have excessive seat pressure. Like the redneck way is to just put super stiff double valve springs and you know, brute force overcome stuff that can cause you know, valve float and surge. But really, that just adds a lot more stress and friction on everything. So JWT's engineered approach actually works really well. Their springs are made out of vacuum degassed Kobe steel. That's stuff that's out of Japan. It's the best spring steel in the world. A lot of the super high-end valve springs are made out of it. It's not only vacuum degassed, but it's electrically refined. So it uses electrolysis to purify the metal. So there's no inclusions in there. Like, any impurities or inclusions could cause a nucleus of stress where a spring can break. And they've done everything, you know, that's pretty much known in the world of metallurgy to prevent that. After the springs are round and heat treated, they're set and then shot peened. For shot peening, like, provides this compressed skin improves the fatigue strength. On top of that, we've gone into the springs and we've cryogenically treated them with CTP cryogenics, and we've WPC treated the springs. So that gives an additional big increase in fatigue strength, life, and failure resistance. So we're hopefully not going to have any valve train problems, even with our drift engine. SR20s are known to kick the rockers off. So what we do is we tip the valves for getting the right installed height. We don't use the Nissan Select Fit shims. And we use Nissan's guide shim on both sides of the rocker arm. Now I wanted to show you those pieces, but I've misplaced them. And when we filmed the first part of the video, we're out of the valve train parts where I was talking about how to make it to fix the rocker arm flying off problem. But guess what? Next day, the parts came, and now I can show you exactly what we do. So if you've raced or messed around or drifted an SR20, you've probably experienced the SR20's Achilles heel, that at high RPM, if you bump the rev limiter too hard or you get valve float, the rocker arm skids off the top of the valves and flies off, and you lose a cylinder. And if you're dumb and got one of those Japanese rocker stoppers, this thing goes sideways, the cam lobe smashes it up, and you bend your valves over, and that's the end of the planet. As you can see, like the stock assembly here has one guide shim and one Select Fit clearance shim. So it kind of goes like this, and the clearance shim is a Select Fit, like Nissan makes a whole bunch of different sizes of these, and that's how you can make it so the rocker arm sits level with various different valve job depths and all that. The way you check it is you get a dial indicator and make sure the heights are the same. But this doesn't retain the rocker arm all that well. So what we do is, here we go right here. So here's the rocker arm and the retainers, but we modify it. So we use two guide shims, and then we grind the rocker arms so the Select Fit shim size also will fit in a guide shim. So since you don't have any way of adjusting the heights to make sure that the pad that runs on the cam is level, we do one of two things. One thing we do is we tip the valve so the valve tip heights are even. We use a valve grinding machine and just cut a little at a time and until everything's even. Or what we do is we get one of these and we grind it using some wet dry paper on the surface plate and sand it in the figure 8 fashion until we get these tip heights even. The advantage of tipping the valve is in case you do toss a rocker, you don't have to have a custom hand ground shim. You can just replace everything and put it back. And almost every time you do kick a rocker, you can find the parts and just put it back. So that's the advantage. If you grind the shim, all your valve tips are the same, but that's not too much of an advantage. So, we face this a little bit and get these tip heights even, and the rocker arm is retained so much better. Like, we've never kicked a rocker arm that's been modified with two guide shims off. So, this is what it looks like without the retainers. One of the other things we do is, this is your hydraulic lash adjuster. And if you have like aftermarket cams, stiffer valve springs, run higher than stock RPM, the plunger on this tends to collapse, and you get more like play in the valve train, which could be enough to get this thing to where it's really easy for it to skip out. So they do make solid lifters and solid lifter cams, but what we do is we use the hydraulic lash adjuster from a roller cam SR20. Now that's found in like a 2000 to 2002 B15 Sentra or a P11 G20 in our country. So these HLAs have a bigger hole on the feed side and the smaller one on the exit side. So they pump up harder and they stay full of oil better and they resist collapse. So these also help you resist getting your rocker arm kicked off. So, we've never kicked the rocker arm off in any of our motors that have had all of these tricks done to them, and they're easy enough for you to do too. So do this, never get a rocker stopper, and you'll fix the SR20's weak point. For timing gears, we're running JWT's adjustable timing gears. And what's different about them, instead of having a bunch of Allen bolts, you have all these letters and numbers machined into the face of the gear. And you do a combination of putting the dowel pin in different holes and jumping teeth. There's instructions that come with this, but you can adjust the cam timing in increments of 2 degrees. And, that's fine enough. And there's no chance of this slipping. And, in the drift engine, you're doing a lot of clutch kicking and shocking the valve train. And, the adjustable timing gears might slip, but there's no way these are going to slip. They also have induction hardened teeth for long life. And they're actually pretty simple. No parts to move or fail. For an oil pan, we're using a Greddy oil pan. SRs have like ridiculously small oil pans and poor oil capacity. So, if you get any kind of oil consumption or you spit in the oil, you run out of oil real quick and then you can spin a bearing. The Greddy pan adds about another liter of capacity. It has these trapdoors and baffles to help keep the oil around the pickup. If you're drifting or road racing, I'd say this is about a mandatory part. Greddy just makes this pretty low priced piece. There's other companies that make the same sort of thing, but we're just using Greddy. For an intake manifold, we're using a Greddy. Now we found that turbo SRs really respond to getting a bigger plenum volume in the manifold. It's up to like 30 horsepower at the same boost level, so that's just like free horsepower that doesn't stress the motor so much. There's a lot of cool manifolds for the SR, like some with fabricated plenums and velocity stacks inside, but the Greddy manifold's actually pretty cheap, and it probably might make 5 less horsepower than a Super Trick billet fabricated one, but shoot, it costs 1/3 as much, so it's good enough. So this Greddy will make more power and with less boost, and it's not too expensive. So we got these super belts from Injuku Racing, and belts are always important. These are like really thin, so you won't get heat buildup when you're running at high RPM. They're also Kevlar reinforced, so they're a lot stronger than stock, so you're a lot less likely to throw a belt and lose your water pump cooling and stuff like that. So, it's not a total part of the engine, but I think it's a cool piece that's pretty inexpensive and important for your reliability. For the ignition, we're running Ignition Projects coils. Now we use these on a lot of our race motors. It's kind of like super easy, way more ignition power. These coils are multi-spark, so they're kind of like an MSD. So for each cycle, they'll spark the coils 6 to 14 times. So you have that many more chances to ignite the fuel-air mixture. They also have about twice as much power as a stock coil, and all the electronics to do all that magic are all in here, so there's no more boxes or anything. You just put these in and they replace your stock coils, and bam, instant, a lot of ignition power. So if you look at the Pikes Peak car that we've worked with Evasive and drift cars, other time attack cars, we always use these things. And, we're able to run a pretty decent plug gap and, boost them to the moon, and we don't have a misfire problem. Like there's other high performance ignition systems on the market, but they usually require a box and stuff like that. I'm not saying that these are any better, but these are sure easier to install and use. And the multi-spark and the more degrees of sparking per degree of crank rotation really improves the chances of ignition. Really like this. I use these on all my personal cars, so we think it's a good choice for easy ignition. One last thing. I know a lot of you might say, oh, I get 600 or 700 horsepower out of my SR20. I mean, it's totally possible. The SR is a pretty strong motor, but we found with extended hard use, like, if you keep the bore to like 86.5 and don't go bigger, they'll probably be okay. But if you bore the maximum of 87 millimeters, we've split the cylinder walls on these things at about 550 horsepower. So, I always say low 500s is really safe, and more is possible. But, when you're road racing and doing long duration power kind of things, I think it's better to err on the side of being conservative. So if you're drag racing, sure, more power. If you're not, like, keep it to low 500s and you should be able to go for a really long time, because the SR is a pretty sturdy motor. So if you like this content, be sure to subscribe. Go to MotoIQ.com. We have lots of tech articles, a lot of SR20 stuff there. That is if you still read. If you need parts, our web store has parts, so you can order like a lot of the parts we're talking about there. And we also have cool merch, so if you like the shirts that I wear and things like that, and jackets and hoodies, you can get it all on our web store. So I hope you enjoyed this, and we'll talk to you next time about something else that's interesting.